Hey everybody, what's going on? We're going to continue our investigation in graphing circular functions in this video. We've looked at how to graph the basic versions of y equals sine x, cosine x, and tangent x already, and we've learned how to graph translations of each of those functions. And now what we're going to do is we're going to focus on stretches and reflections of, specifically in this video, y equals sine x and y equals cosine x, and then in another video we'll do the same thing with y equals tangent x. Alright, a lot to discuss here. We're going to focus on the stretching first, and I'm going to relate this again to what you learned in chapter 1 regarding what you do to the input or the output of a function in order to make either a horizontal or a vertical stretch. Alright, and so we're going to use y equals f of x kind of as our parent function and show what do you do to it in order to make one of these two types of stretches. Now, turns out that whenever you want to get a horizontal stretch of a function, what you would always do is you would multiply the input value x of that function by some kind of constant value. And so in chapter 1 we just said you multiply the input by a constant value q, and we said the equation then for a horizontal stretch was y equals f of qx. And a little bit more specifically than just saying that gives you a horizontal stretch, whenever you multiply the input value of a function by some constant q, it stretches that function horizontally by a factor of 1 over q. And that same concept is going to work with y equals sine x or y equals cosine x. So examples of equations of each of those things that would be horizontal stretches, if I had y equals sine of 6x, well, that's a horizontal stretch by a factor of 1/6. Now the stretch factor tells you whether you're getting bigger or smaller, and so when we say the stretch factor is 1/6, that means horizontally this thing is shrinking. Alright, it's becoming more narrow instead of wider. Okay? Now let's look at one that would stretch and make itself wider. That would be something like y equals cosine of, say, 2/3 x. Alright, and here I get to emphasize that the stretch factor is just the reciprocal of whatever that value q is. Alright, and whenever that value q is less than 1, then that means the stretch factor is going to be greater than 1, and so that tells you that the graph would get wider instead of narrower. Alright, so that's horizontal stretching, and that's when you multiply, again, the input value of a function by some constant. Well, when you multiply the output value of a function by a constant, it gives you a vertical stretch. And in chapter 1 what we said is that then if we multiply specifically by the value p, if we multiply the output value of a function by the value p, it gives us a vertical stretch. Okay, and so p could be any constant value, and the stretch factor for multiplying the output f of x by a constant p is p. And so a quick example of an equation of a trig function, a sine or a cosine specifically, that would be a vertical stretch. You could have something like y equals 17 sine x, which would have a stretch factor of 17. And when we're talking about vertical stretches, whenever the stretch factor is greater than, well, whenever its absolute value is greater than 1, it's going to make the graph taller. And if it was the absolute value of that stretch factor was less than 1, then it would make the graph shorter, essentially. Alright, now I need to be even more specific than this, but you've got a good general idea of how you affect the equation of a sine function or a cosine function in order to make either a horizontal or a vertical stretch. Okay, and when I say I need to be more specific, I'm going to break each of those things down, and I'm going to tell you what special aspect we can say changes whenever you have a vertical stretch versus a horizontal stretch. Alright, now for vertical stretches, we're talking about affecting how tall or how short the graph is, right? So from the bottom to the top, that's what the vertical stretch affects. And we have a measurement with trig functions that describes how far it is from the bottom to the top of the function, and that's called the amplitude. And so whenever we're working with a vertical stretch, what a vertical stretch is going to do for y equals sine x or cosine x is it's going to change the amplitude of the function. Now it turns out to be really easy to look at the equation of either of these things and determine what the amplitude is. Let me write the rule for you right now. I'll tell you what the amplitude of y equals a sine x or y equals a cosine x is. Quick note, whenever we were talking about vertical stretches a moment ago, I said you multiply the output value by some constant p, and that's what we used back in chapter 1, that was what the textbook tended to use, was the letter p. Here, we're going to use a, but it's still multiplying the output, the sine of x or the cosine of x, by a constant value. We're just going to call it a, which is kind of nice because amplitude starts with a. And the way you determine the amplitude is with that value a, what did you multiply the output values by? And simply the amplitude is always going to be equal to the absolute value of a. Alright, we've only looked at positive values of a so far. We'll look at negative values of a later on. But nevertheless, the amplitude of either of those functions is always going to be the absolute value of a. Now, let me show you the effect on the graph of y equals cosine x when we change the value of a from 1, because that's what it would be implied to be here, to 2.5. Alright, so you see the graph of y equals cosine x already there in green, and what we're saying is going to happen when we change this value of a, we're going to get that vertical stretch, and it's going to change the amplitude, and it's going to change it to the absolute value of this number, which would be 2.5. Now, how does that affect the way that you're going to graph this function? Well, all it means is that you're going to take the maximum value and the minimum value and multiply them by 2.5 essentially, okay? So whereas y equals 1 cosine x, its maximum value is 1, whenever we're working with y equals 2.5 cosine x, its maximum value is going to be 2.5, alright? Now the intercept will still be 0, and then the minimum value would be negative 2.5. See how that works? So we're just changing where the maximum and the minimum values are essentially. Now when we throw in translations, it'll change the central value. Well, no, it won't ever change the central value. Okay, so there's the first half of the graph. You see it only changed the height, it didn't change the cycle. We still have one full cycle of values between 0 and 2 pi. And here's the left half of the graph. Voila. Alright, so the vertical stretches affect the amplitude of a sine or a cosine function. What about horizontal stretches? Well, the horizontal stretches change something different. It changes how narrow or how wide the graph is, we've said. And whenever you're changing how narrow or how wide the graph is for one of these types of functions, it turns out that you're changing what was called the period of the function. Because remember, that was kind of our horizontal measurement, is what is the length of one cycle, or what is the period. And we've been saying the period is 2 pi for y equals sine x and y equals cosine x. Well, we're going to be changing the period whenever we stretch horizontally for one of these functions. Now this idea takes a little bit more time to catch on to than the vertical stretch changing the amplitude idea. But let me go ahead and share the rule with you for how a horizontal stretch affects the period of a sine or cosine function. Now another quick note, as far as notation goes, whenever we were talking about horizontal stretches a couple slides ago, we were using the variable q and saying you're multiplying the input value by some value q to get a horizontal stretch. Well, instead of the letter q, we're going to use the letter b in regards to horizontal stretches of sine or cosine or tangent of x. Alright? And so, no difference there. Now, here's what the number b actually tells you. I'll let you know. It tells you how many cycles a sine or a cosine function will go through on the interval from 0 to 2 pi. So, for instance, down here, where the b is equal to 1/2, that means we would experience half of a cycle between the values 0 and 2 pi. Now, I'm just trying to lead you to kind of understand this a little bit. If you know how many cycles you have between 0 and 2 pi, and you want to find out what the period of the function is, well, all you have to do is take that 2 pi and divide it by how many cycles there are going to be. Alright, so really 2 pi divided by the absolute value of b, because b can be a negative number, although it typically is not. And I want to show you how that plays out then on the graph. But this is a little formula you need to know, essentially. Whenever you're calculating the period of a sine or cosine function, you always do 2 pi, the period of a normal sine or cosine function, and divide it by whatever the value of b is. Alright, so you got the graph of y equals sine x there, and you know that the period of y equals sine x is 2 pi. What we're getting ready to do is we're going to graph y equals sine of 1/2 x. And since that's going to change the period, we need to calculate what the period of y equals sine of 1/2 x would be. And we're going to use this little formula over here to do that. So we would simply say that the period is 2 pi divided by 1/2. Now that's the same thing as 2 pi times 2. If you multiply by the reciprocal of 1/2, you get, alright? And so that means the period of this function happens to be 4 pi. So it would have to go all the way from 0 to 4 pi, somewhere way over here, in order to go through a full cycle of values. Okay. Now discussing the period is one way to discuss what is the effect of how much wider, in this case, this graph is going to be because of the horizontal stretch that we had. Another way is to think of this. If the stretch is, or if the input value is being multiplied by 1/2, we know that the stretch factor is 2, which essentially means this, that every point that's not on the y-axis is going to get stretched to twice as far from the y-axis as it began. Okay, stretch factor is 2. And I think that'll make it easier for you to understand what I'm going to do as far as changing this graph here. Alright, so this point's not going to go anywhere, and in fact, we're just going to go ahead and plot the initial point for y equals sine 1/2 x there, because it's still going to start at the middle value or the intercept. But then this maximum value, it's going to end up being twice as far away as it began. So here's where the maximum value would be. And then this intercept will be twice as far away from the y-axis as it began. So all the way over here at 2 pi is where the next intercept value would be. And then it turns out that this minimum value, well, it would end up being 3 pi over 2 times 2, or 3 pi units away, and that's going to be outside of our negative 2 pi to 2 pi range that we're going to be graphing. So we only got half, ooh, that's ugly, we only got half a cycle of the sine function between 0 and 2 pi here. And remember, I told you that's what this number tells you directly, is how many cycles does the graph show you between 0 and 2 pi. Okay, now let's go ahead and look at the other half of the graph. This minimum value here, it would get stretched out twice as far as it was, so it would get stretched out to negative pi. And then this intercept, or this median value right here at negative pi, would get stretched out to negative 2 pi, twice as far from the y-axis as it began. And so you see we also had one cycle between 0 and negative 2 pi. Alright, and I'll kind of summarize it this way. We said that the period of this function was going to be 4 pi. Well, it turned out in this case it took all the way from negative 2 pi to positive 2 pi in order to get the full cycle of sine values, didn't it? Where we got all the intercepts at a minimum value and a maximum value. So, indeed, the length of that one cycle was 4 pi units. Excellent. Now, one more concept I want to discuss with you, and that's the concept of a reflection, and in particular, a reflection in a horizontal line. And then I'm going to try to put these three pieces together. Alright, so we're looking right now at functions that are in the form y equals a times sine of bx, or y equals a times the cosine of bx. And what we haven't looked at yet is what happens when a, or b for that matter, but we're going to focus on a, when a is positive versus when it's negative. Alright, you might remember that you can reflect a function in a horizontal line simply by multiplying it by a negative value. Alright, so anytime a is positive, such as in y equals positive 3 times the sine of 2x, you know how to graph that kind of thing now, don't you? And you know specifically the pattern, because I'm going to discuss the pattern of the points in the sine function and in the cosine function for when a is positive. Alright, in the sine function, you know you start at the middle value or the intercept. And then you go to the max value, and then you go to the middle value again, and then you go to the minimum value, and then you go and finish at a middle value again, right? Well, what's going to happen whenever a is negative is that's going to flip. Alright, now the middle values are going to remain middle values, but where you would have graphed a maximum value, if a is negative, you would instead graph a minimum value. Alright, and then the middle value again stays the same. Where you would have graphed a minimum value, now you're going to graph a maximum value, and again the middle value stays the same. I'll go through the same thing with cosine in a moment, but let me go ahead and show you an example with the specific sine equations that I have down below. Now, I want to explain the graph that I've already got. I've made the graph of y equals 3 sine 2x, and you ought to be able to see the vertical and the horizontal stretching in full effect here. You can see that the amplitude of this graph is 3. From the central value, it goes up 3 units to its peak, and it goes down 3 units to its trough, I guess you could say. And you notice there's 2 cycles between 0 and 2 pi. Here's one cycle from 0 to pi, and then from pi to 2 pi is a whole nother full cycle of values, right? So the stretch factor of 1/2 meant we made each cycle half of what it used to be, and so that made more cycles within that interval of 0 to 2 pi. Okay, made the graph thinner, as what we said. Now what we're going to do is we're going to graph y equals negative 3 sine 2x, and all that's going to do is reflect in the y-axis, in the x-axis. Now let me do that describing the pattern thing that I was talking about. We're still, when a is negative, going to start off at an intercept or a middle value, but then instead of going to the maximum value, we're going to go to a minimum value instead. And then we'd go back to the middle, and then instead of a minimum value, we'd go to a maximum value, and then be back to the middle value. So here's one cycle of this function. Just a mirror image, right? Okay, now let me just continue that pattern throughout. There's the rest of the positive half of the interval that we're trying to make. And now the graph is complete. Just mirror images in the x-axis, or in a horizontal line is really the way I want you to think about it. So that way when we throw in translations, you'll still understand what's going on. Okay, you've seen the effect of a horizontal, a vertical stretch, and a reflection in a horizontal line, and you've seen how to change the equation to make each of those things. I guess the only thing I haven't described yet that I need to real quick is what is the pattern for when a is positive and when a is negative for a cosine graph. Let me fill that in real quick. Remember with a cosine, you start off by graphing the maximum value, then a middle, then a minimum, then a middle again, and then a maximum value. That's when a is positive. So if a is negative, it's just every max is going to change to a min and vice versa. So the pattern would be minimum, middle, maximum, middle, minimum. All that's left for us to do now is to go ahead and just try one of these equations from scratch, because all I've done so far is given you one graph and shown you how to change a very slight bit in order to get another graph. Let's say we don't have any graph to begin with. What we're going to do is we're going to sketch a graph of y equals negative 0.75 cosine 3x. And we're going to do so as we usually do on the interval from negative 2 pi to positive 2 pi. Alright, and some things to discuss before we even really get into trying to plot any points here. And those are the 3 values that we said change whenever you have any kind of stretching or a reflection. And we're going to have all 3 of those things in this equation. First of all, you need to know what the amplitude is. And we said the amplitude is always equal to the absolute value of a. Well, here a is negative 0.75, so the amplitude would be positive 0.75. Now, on my graph, one of the things that's going to affect is the intervals I use on my vertical axis. In this case, we're going to 0.75. I think I'm going to go ahead and put my positive 1 way up here so that this would be 0.75 right there. Okay? And then I'll put my negative 1 in the corresponding position down below. Our graph is definitely not going to get higher or lower than that. Then the next thing we need to consider is the period of the function. That's determined by b. And remember, what you do is you divide 2 pi by the absolute value of b, so we do 2 pi over 3. That's how long a period is for this function, is 2 pi over 3 units. Alright, and then the pattern. It is a cosine function, so typically we would have started at a maximum value, but since a is negative, we're going to start at a minimum value, so we'll get this sequence. we'll be starting at a minimum this time and finishing with a minimum with a maximum in the very middle of the cycle. Now let's go ahead and start with that. We can plot our first point, which is going to be a minimum value. We can plot it because it's going to be on the y-axis. There's no horizontal stretching to worry about for that. So let's go ahead and plot a point at the minimum value, which would be negative 0.75 due to our amplitude right there. Now let's tackle that horizontal stretch problem. And here's the way that I'm going to attack it. If I know the period is 2 pi over 3, then I know the first cycle of this graph, instead of going from 0 to 2 pi, is going to go from 0 to 2 pi over 3. And so what I'm going to do is I'm going to figure out where is 2 pi over 3 on my horizontal axis, and that will tell me where the first cycle will end. Now notice I've got basically 1/4 pi, 1/2 pi, 3/4 pi, and 1 pi right here. Well, 2/3 pi is going to be between 1/2 pi and 3/4 pi. It's going to be a little bit closer to 3/4 pi than it is to 1/2 pi. So I'm thinking right about here is where 2 pi over 3 is going to be located. I'm just going to put a little slash right there. And then I'm going to go ahead and teach you how to graph the first cycle, the first complete cycle of values here. Alright? Now, we know that 1/4 of the way through our cycle we're supposed to get to the middle value, or to a middle value, right? So, if you're thinking about what's 1/4 of the way from here to here, we could estimate that. Well, we can calculate that, but then we can estimate where that fits on a graph. 1/4 of 2 pi over 3 is 2 pi over 12, or 1 pi over 6, right? And so let's figure out where we think 1 pi over 6 would be, and that's 1/4 of the way through our cycle, and we'll put our middle value there, somewhere maybe around right there. All right, and then at pi over 3, we're going to have our next our halfway point essentially. Now we're just estimating that again, and at pi over 3 we're going to get our maximum value, so that's going to be about right there. Then we'll have our intercept somewhere around here, and then we'll finish the cycle at 2 pi over 3, and we finish the cycle according to our pattern with a minimum value, right? Now I said this first cycle ended at 2 pi over 3, which means the next one would end up 4 pi over 3, and then the one after that at 6 pi over 3, or 2 pi. And so let me make note of where 4 pi over 3 is. It'd be a little closer to 1 1/4 pi than it would to 1 1/2 pi, right? And so then we'll try to divide that in fourths to make our next cycle. Really just eyeball this the best you can. You figure that halfway through the cycle you're going to have your maximum value, and that could be about right there. A quarter of the way you'd have a middle value. 3/4 of the way you'd have a middle value, and then at the end of the cycle you'd have a minimum value. And then repeat from 4 pi over 3 up to 2 pi. Now remember, this number is supposed to tell you how many cycles you have between 0 and 2 pi, and you can see we went through 3 complete cycles of that cosine function between 0 and 2 pi. Now all we've got to do is kind of reflect that, since a cosine is an even function. We're going to reflect that in the y-axis here, or just trace the pattern backwards really. Negative 2 pi over 3, negative 4 pi over 3, and negative 6 pi over 3 would be the ending cycle values, or beginning cycle values, however you want to look at it. And so I'll go ahead and fill in the rest of the graph. Voila, there it is. Now, was this easy by any means? No. Is it going to get easier when we start throwing in translations along with the reflections and the stretches? No, it's going to be pretty tough, but you understand the basic principles and how each of the numbers that we're throwing into these equations kind of affects the graph, whether it's a stretch or a reflection or a translation. Alright guys, thanks for your attention to this video, and I appreciate your diligence in completing the related assignments. See you in class.